to VCF. I really wish we could be together, but yeah, that's for another time, as we were just speaking. As Helvig mentioned, I was a PhD student at Bergen not too long ago, and I was sort of just searching through my photos last year, and I found one of those funny Christmas cards where we were on sale on a Christmas catalog with others from the team. Yeah, my research at that we started with Helvig as my supervisor is on looking at the integration between computational tools and how visualization can be a facilitator of the interaction with computational methods. I mean, more, and then I've sort of also looked into, and I briefly talk about today, into different perceptual cognitive mechanisms that we have, and then how visualization, how we can understand, how we need to understand those mechanisms to approach visualization. And today I'll have some case studies. I'll present some case studies and their applications sometimes in biology, cybersecurity, and social sciences as well. Right, I'd like to start by setting some sort of terms and then how I talk about these terms. So I sort of, since data science is a term that we all sort of relate to, and it's sort of in my abstract and title, the way I see is data science, or the way we talk about data science, is a process where you start with, at least the practice of data science, a process that you start with formulating questions that can be answered with data, where you iteratively collect, clean, analyze, model. But while doing so, you're sort of communicating and interpreting and taking decisions, like acting on the outcomes during the iteration. But when thinking of that process, I like to think of that process more and more about this interactive process where the human, who could be the analyst, who could be the interpreter, who could be just the consumer of the results, the human with different forms of the data, with different representations of data, and then the algorithms that are trying to sort of summarize the data or sort of represent or model the data are in continuous interaction. So I like to think of the data science process as this interactive process. Just want to put some sort of interfaces that we've sort of worked with in the past together also with Helvig, is that we sort of look for ways of incorporating computational methods in this interactive process, where we provide visual interfaces to the data and visual interfaces to the algorithms which respond to some interactive input that are coming from the user. So I'll have some examples of these interfaces later on in the talk. But then the question is always, this question always comes, like, automation is great. It's pretty good. I mean, we've seen like the machine learning techniques, deep learning techniques achieving like great feats. So why do we still need a human? Well, so why don't we just leave it to the models, leave it to the algorithms to do the job for us? So why is that need to have some human input and human touch to that whole process, and why that interaction is important? I'm sure you have seen these sort of this chart already in a few other talks, but I still quite like it. I mean, I just want to present a few reasons why I think we still need the human in this process, in the data science process, because models will always tell you a story. They'll take in data, and then they'll act on it, and then give you some results, like these sort of super funny and then super sort of now I think almost famous spurious correlation web page with lots of these different correlations, but there is actually not much really a correlation. But if you just plug this data into a model and if you get a number and then you want to make a decision on that single number, which is, let's say, the temporal correlation of the correlation between these two time series, you might think that there's a relation between cheese consumption and number of people dying, becoming tangled in their bed sheets, and that's not something you want to do. That's where you need a human interpretation. And as all of you have, you might experience when you engage with some modeling, some data science process, there are lots of decisions to make. There are lots of algorithms, lots of parameters, lots of settings, different aggregation levels, and all of those have an impact on what you get in the end. And then here's sort of one decision tree from the Python machine learning library scikit-learn. You see that there are these guidance, sort of some sort of guidance, some rules to choose the right tools, but this is not always definite. And each decision that you make on this journey to sort of choose a technique has a different implication. And all of these tools will tell you something different, which brings me to my sort of next point. I don't know if you know the movie by Kurosawa, the Rashomon. It's an interesting movie where there's an incident in the beginning, and then the movie is about us as the viewers of the movie, like hearing the incident from several different people that have sort of seen. There's some murder happening in the woods, if I remember correctly, and then everyone witnessing that tells us a different story, and then we as the viewers haven't seen the actual event, but we need to construct what we believe in based on the stories that people tell. That's been like coined as the Rashomon effect in this really amazing paper by Leo Breiman, the statistical modeling the two cultures. What he talks about the Rashomon effect in the context of modeling, in the context of data science, is that there will be a multitude of many models that have that give you very different descriptions of what's important in the data, even though they are equally good. So, I mean, he gives an example of multivariate regression models, each having exactly the same error rate, each having exactly the same effectivity in predicting the outcome, but they all pick up on different variables, so they with different weights. So if you look at picture one, it values some variables. It explains the outcome in a different way, but they're all equally good. So in the end, you need to hear all of these views that comes from different models, and then like harmonize them in one decision yourself in the end. And the final sort of reason I just want to say is that the phenomena that we try to model is always complex, and we need to understand and relate to the data, relate to the models that we built and that we use. I really like this quote that we heard from our collaborators in a project with the social scientist collaborators. They were saying that as social scientists, they need database models that they can understand and explain to their peers in full confidence. And that's another very big motivation, that we need to create this interaction between the data and the models and people, so that they build an understanding of what's going on in the model. At the end of the day, I mean, that's not the only role of like computational models, but that's a very big role that they need to play. We need to understand, and we need to turn what we learn from these models into actions and into explanations. So that's where this scope for these human data algorithm interactions come into play. And then in that context, I would like to sort of talk about carve out this space for visualization. This is what the area that I'm interested in as the facilitator of this interaction between these different components. I always like to refer to the definition of visualization by Tamara Munzner, who says the computer-based visualization systems provide visual representations of data sets designed to help people to carry out tasks more effectively. And then there are some key bits that sort of relate to what we are doing. Like this of course, we are operating on different data sets, but it's also about people doing tasks, and visualization is a facilitator of that task completion, getting certain jobs done process. And then, yeah, we've seen visualization being used for various in various different roles. Like one common role is for presentation that we usually see in the media, like it's a presentation communication device for data. But we are also seeing visualization especially in the field of visual analytics being used for analysis quite often. This is maybe for a more expert audience trying to analyze the data, try to sort of interactively use certain models to both better understand the data, but also to better model the data. So it is that it's not necessarily this or that distinction, but it's sort of there are these sort of slightly distinct roles for visualization. So I want to show some case studies and examples where visualization is facilitating such interactions between human data and algorithms by providing several perspectives concurrently and supporting the interactive comparison and evaluation of several models and several representations of the data. But with several models, or several perspectives, what I mean is like multiple data sets, scales, multiple parameters, algorithms, and representations. Right. So want to sort of just go over some case studies where in my research together with lots of my colleagues try to explore this space of interactive visual data science. The first one is from a few years back. You'll see that Halvik is also on this like we collaborated on this work together with him as well, where we wanted to look for where we had some spatial data, geographical data about some survey data that was done in the UK that span across the country, and the interest here was on understanding the interactions between multiple variables, multiple indicators over space. And then we know that like in any multivariate data set like this, in this case, sort of these are some indicators of the populations, as the demographic indicators like the age population, the ethnicity, sort of distributions, what industry people are working in. So these are all variables trying to describe the different areas and then statistics about those different areas. What we wanted to do is, but we know that these relationships and the proportions of these and the relationships between those variables, attributes change over space. That creates a sort of an immense space for exploration. If you want to build a single model, that model will be an aggregate model, and that model will not have the sort of the local variations that cannot represent the local variations that are happening in different places over the country. So we sort of, I'll show a very brief video. We sort of tried to address this by some interactively computed localized statistics technique, where we sort of gave interactive tools to explore the space of multivariate relationships along some of the traces that people are drawing on the map. So rather than looking globally at the interrelationships between the variables, we asked ourselves how can we provide the users some means to sort of focus on some localities, and then we analyze the relationships in that space. So what's happening here is that through that like interactive interface, the analyst sort of chooses a trace, an area that's sort of interest, and then as this interaction is happening, some computations, some statistics are computed in the background, and it's trying to show like the response of one single variable at a particular location in response to the others. So by sort of looking at these small multiples of different traces of the different variables, we sort of try to support this multivariate comparison task. We then looked into in another work. So this was about like primarily about like the location, and then we asked ourselves, so what about the different aggregation levels, because that's another decision that you make when you're analyzing. So if you're interested in understanding the relationships between multiple variables at different aggregation levels at different scales, how does it look? Here is a sort of a simple explanation, simple example of what that problem looks like. So we are looking at, on the left, average household electricity consumption. On the right, we are looking at average gas consumption. And these are sort of just the distributions. And if you are interested in some bivariate comparison, what we will use is a bivariate correlation function, and then to sort of try to explore the relationship between those two variables, electricity and gas consumption, over space. So we see that in places where there is more electricity consumption, there's less gas consumption, as you can see on the right map. This is because the heating is by electricity, etc. And then there are sort of similar places like that, mostly rural areas. But then in some other places, that relationship is it's sometimes reversed. It's either a bit more stronger, weaker. So that relationship, that dynamic is changing all the time, where you move between the country. So if you look at the data in a scatter plot like this, like if you discard the geography and then just look at the relationship between electricity consumption and gas consumption, what you get is a relationship like this, and you get a single correlation coefficient value, right? It's -32, and then that could be that measure that sort of tries to capture that bivariate relationship. And if you then go and then put this on the map as -32, because that's a single value, what you're claiming here is that relationship is the same across everywhere. But we've already seen that it's not the case. So that's a phenomena that varies depending on where you're looking. So in order to sort of counter for that fact, in spatial analysis and spatial methods, there has been some geographically weighted techniques proposed. One technique that's been around by Chris Branston and colleagues, that was presented in 1996, was the geographically weighted regression. What you do is that for each location on this spatial map, you just consider the locality of that region. So instead of computing a global measure, you visit each location on this map. In this case, like we have 326 areas. So you visit each 326 areas and consider neighborhood at different levels. So what we are seeing here is that as you increase the locality of this measure, we see that around London, so the relationship is very different. There's a very strong correlation between the two variables. Like in Southwest England, you see that's quite different. That becomes even more negative. So the more local you look, the more variation it reveals in a way. So this -0.32 is not global at all. Actually, if you look at the map, you might not be seeing -32 at all. But that's the thing about aggregations. And then, of course, we ask ourselves, okay, if we know that that these relationships vary, and then we know that there are many of those variables, so it's not just two, then the problem becomes quite complex. So how do we then sort of explore the interrelationship between all these variables at different aggregation levels, at different locality levels, at different scales, concurrently? So, but then you run into this problem. So you have many variables, you have many scales that you want to explore the relationship between those variables. And then there are also, of course, both spatial and then non-spatial. So it's a sort of a complex problem. And then here is one illustration that sort of shows that kind of like complexity. So we've sort of developed some visualizations where we where we are looking at the bivariate relationships of a large number of variables, both over the map, but also over scatter plots. We had this sort of the distance metrics where one diagonal, or sort of correlation metrics where diagonal is maps, and then the other is about the scatter plots. But this still, I mean, this still meant that we have so many different aggregation levels. This hasn't still solved the problem of how do we represent these the changes, like in response to the locality between the relationships. And then we sort of came up with some simple visualization where we want to just compare through some glyph representation whether in what direction the relationships change when you apply different aggregation levels, like how much there's a change if when you're looking at globally versus locally. So we sort of came up with a design like this where so you are looking at like each level in this sort of square graphic is a different aggregation level. So you start from the local representation to global representation, and then you explore whether it's getting stronger as you sort of look at it globally, or weaker, or if it doesn't change. If it doesn't change, it means that it doesn't really depend on the locality that you look at things. So then we sort of integrated this representation in a single sort of like a matrix, like on the left, that shows many variables at many scales, and then shows their changes in response to the aggregation levels. And then this was integrated with some interactive interface where we sort of explored how these relationships are sort of seen. So this was sort of then, I mean, then we were able to sort of scale this to sort of many variables, and then we also, we just go forward a little bit, yeah, and then we sort of use those sort of glyphs in an interactive interface where through interaction users are able to sort of explore the multiple aggregation levels and then see how the sort of the statistics respond to that. So a few observations from this is that through these interactive representations, we are able to relate multiple scales. So we to each other, we are able to see multiple variables and multiple locations, and then visualizations enable us to sort of see these different variations concurrently, and then interaction brings out the exploratory capabilities to look at these several alternatives at the same time. So I want to move to another case study where we looked at, which is in a very different domain, where the interaction is also a bit different. The users in this example are not necessarily trying to build a model or sort of analyze some sort of correlation relationship, but rather they are here to make a decision using some recommendation from a computational model. So that's a different kind of interaction. This is within the context of an EU project where we looked at some cybersecurity systems, data coming from cybersecurity systems. The goal was to sort of to support the task of user behavior analytics, which is an area that's becoming increasingly popular. What you try to do in these user behavior analytics systems is that you sort of collect data that your users are doing in digital applications, like you collect logs of user actions over time. In this case, we worked with our partners in Amadeus, and this was data about their user management system that's usually used by their IT staff. So what you have is in a single session, the users are sort of using a digital application. They're doing some action, like their search. As the data and the examples I give are coming from a user management software. What they do is that things like searching for accounts, unlocking an account if it was sort of locked, or sort of locking an account, or doing some sort of user management kind of tasks. So in this sort of application domain, you end up with these sessions of user activities, and each session is a series of actions. And then the goal of the user behavior analytics model is to look at this session and try to understand whether that's an unusual action, whether the sequence of actions that are featuring in this session are unusual, are somehow suspicious. Of course, and then what the model tries to do is to give a score for this session, and then the cybersecurity analysts try to sort of make some sense of that score. So in the end, what they are trying to do is to sort of look at all these sessions and the series of actions, and then try to decide, try to understand the user behavior. Is this a usual user behavior in the session? Is this unusual? If it's unusual, why it's unusual? Which is a complex question in its own right. So we are looking at, in this particular case study, we are looking at a month's data with 15,000 sessions, 1,400 users, and 300 action types. And just to sort of help you a little bit in the next few slides, the way we represent, you can visually think about this session is that, so it's a timeline of activity, and at different points in that timeline, different actions happen. And then we see this, so that's these are sort of colored by the action that we do, and then we did some sort of semantic distance-based clustering to sort of reduce the 400 types of actions into a smaller set. So each color represents a different kind of action, and then they're sort of as represented as ticks over time. And then we have the score that's coming from the algorithm that the application partners have. And then, yeah, I'll use this representation in the next slides. So what we did was sort of to represent this a bit more simply, where we sort of preserve the sequence that's in this timeline, but we drop the actual time. So we just represent the sequence. So we have these two kinds of representations that I will use also in the next slides. And then the most important decision to make with the help of an algorithm in this context is how expected is such a session like this, given that the user has done all of this before. So that's the context that the decisions has to be made. But then you ask this question, and then the algorithm gives you a number, and that's what they were trying to work with. The algorithm says 0.7. And that was a score between 0 and 1, 1 being the very unusual, very sort of suspicious. But how do you act on that? That was the biggest problem. Should you just lock the account? I mean, what they were doing was to sort of open the data in an Excel and try to make a decision. That was really problematic. And then the actions they take as a cost, if it's something is unusual, they lock the account, and then if they lock the account, that's the customers that is sort of staff members that are getting quite annoyed for that action. But in order to respond to that question, there are lots of facets to think about. Are the actions in this particular session are indicative of some problematic behavior? What kind of tasks the user might be doing? Because there's some semantic sort of sequence to that. Is this a usual session, like given that what this user has done in the past? But is this a usual session if you think of all the users that have similar roles in the organization? And then, or does this fit in the role of the user? Or sort of what is common for a user of this role? So there are all these facets to that data that you need to understand. And the score of 0.7 is maybe computationally representing some of this, but it's giving you nothing away of these complexities that went into that number. So what we thought that we could support this process through visualization by giving this multifaceted, more comprehensive understanding of user behavior, and then put that number, put that sort of recommendation in the context. And of course, this data was sort of complex, and then that's sort of like big, and then visualization alone was not sufficient. So we sort of went into using some computational techniques to extract some sort of high-level abstractions of the data. We used like a topic modeling technique coming from document analysis to sort of extract some high-level tasks from the sort of the atomic actions that people are doing. So we try to find these sequences that are sort of regularly emerging in the data. And then what we had to do for that, I'll just skip this part a bit quickly in the interest of time. So we sort of turned those sessions into documents, and then we did some document topic modeling analysis, which gave us some sort of topics. And each topic you can think of as a collection of actions that occur sort of distinctively together, that happen sort of regularly together. And then we said these topics then give us some sort of tasks, some sort of common sort of more coherent tasks that people need to do within this data set. And then so this computational process, they gave us some topics, and then we sort of labeled them as tasks, as I mentioned. And here is some visual representation of those topics. So for instance, number 6 here is like create user, assign role 1, assign role 2. These were some of the granular actions. But then this group of granular actions, we thought, I mean, this looks like a user management task that someone is doing. Whereas number 11 is a combination of search behavior and unlock behavior. They search for an account and unlock the account. So this is like a help desking task. So the sort of these combinations of these actions become the tasks. And then we sort of relate these task summaries like this. So this is a task summary of a single individual that does like number 9 a lot, to the history of those users. So in the top one, we're looking at the sessions from a single user, and then their summary, task summary. And on the bottom, that's another user. So we see that there's the top one is the user with a very dominant task. So they've always been doing number 12, which is that search and unlocking behavior, which is likely to be a help desk person. Whereas if you look at the second user, or their sessions are quite varied. They do all sorts of things, and then that's sort of revealed also in their task profiles. And then we see that that's a diverse user that will be very hard to model as well. And then, of course, we wanted to reveal user profiles where we have some historical data. Like we sort of visualize so each row in this one is a user, and then we sort of get the data of each individual user and created some historical data profiles for these users. And then we positioned some of these selected sessions that are potentially unusual, and then we put it in the context of the history of that user. So rather than putting like looking at each individual session in the context of all the data, we want to look at locally attached to that user. Yeah, these are like the sessions of interest overlaid on the historics of the user. You know that there's been like several sort of layers to that, and I'll show how it comes together in a second. And then another layer, we said, okay, now we have these different users with different user profiles, so why not look at extract some roles? So we created like we did some clustering on these user profiles that we created, and then try to sort of come up with roles. And then we wanted to present each user within the role that they are, so that they belong to according to the data. So what this sort of enables us to do is to sort of put each individual session in lots of different contexts. So the session that we see here is presented in the context of the chosen user, and then we are looking at so you're seeing that this one is an unusually long session for this user. So if you look at the history of this user has always had short sessions, and this is unusually long. And then, but yeah, it looks normal according to some of the things that this user does, like the starting time is normal. But then, yeah, when you look at it, yeah, this is a normal task for this user. So if you look at only the duration And then that's what the algorithm usually does. It can be flagged as unusual, but if you look at it, that's something that this user always does. And then if you look at the group that this user belongs to, that's also a common task for the group of that user. So in a way, what we sort of try to manage to sort of support is through this interactive interface is to relate these multiple levels, multiple facets of the data to one another. So a few observations here is that context is really key in making decisions. And in this case, like what's the user, what's the role, session. So there are all these multiple levels, and you can only like grasp a fully understanding of what's going on by looking at all these levels at the same time. And also what we have seen is that the enriching the data through some computation, in this case, clustering and topic modeling, has been quite key in this process. So I know that there's not too much time left. I sort of just 8 minutes to 11 in Bergen, but I want to sort of just briefly talk about that second part that I'm now also becoming increasingly interested, is that how do we consider the human in this loop? How do we understand the user? How do we understand the human, and how we account for the human in this loop? And one work that we did, like we started at the end of my PhD in Bergen, and then I sort of followed on later on with other sort of collaborators, is that looking at progressive techniques in this analytical process. What we know by some studies in HCI, early HCI. So if you are having interactive interfaces like this one, where there is some sort of interactive responses coming from the system, you need to sort of maintain a certain level of responsiveness so that your users, the people, is still able to follow, so they're not sort of completely detached from the process. So there's some like fantastic theory that was suggested by Stuart Card and John McKinney and George Robertson, was about this concept of human time constants. So if you want people to process and interactively updating information like an animation, you need to refresh it at a rate of 0.1 second. And if you want your users to be part of that process, the system needs to give a response, some immediate response in 1 second, and then it's a maximum within 10 seconds. A certain task, a certain minimal task has to be completed. Otherwise, just you lose people, so you lose their attention, and then that interactive loop between the algorithm, the data, and the human is broken. So that was quite an interesting revelation. That, I mean, it's not only about the computation, but it's also about the people in that process. So we sort of come up with an interactive process where, instead of forcing to wait for an interactive computation to finish, we want to present a best possible result within that acceptable time frame, with an acceptable meaning that's informed by this table, an acceptable time frame where the user needs to be given a response. So I'll not talk about the details of that, but we've sort of developed some different algorithms, different levels of operations, and different visual representations where we can maintain these levels of perceptual processing in an interactive process. And then, like more recently, I've sort of looking into the more human side of this. Like, I mean, how do we know what we think that people are perceiving from the visualizations are really perceived by the people? So in a study on spatial autocorrelation, and it's about like whether there's a spatial relationship between two variables or not. We did some empirical studies of different representations, like grid map and then different map, and then we systematically tested how do people perceive increasing levels of spatial correlation, and do they really perceive at the level that we assume they will perceive. And then it, like in another very recent paper, which is just published, we explored how do people verbalize what they see, how they can use natural language to express what they see in a visualization. And we asked them to describe the relationships they see in scatter plots of varying correlation. And then we also gave them, in a second part of the study, we gave them a description, like there's a positive correlation between A and B, and asked them to sort of check all those charts where they see that they think that it matches to that description they have been given. And then we sort of got lots of natural language representations of what people see. And then we sort of analyzed that data to understand how people interpret and internalize the information they see from visual representations. So what we are trying to do, what I'm really increasingly more interested in my recent research, is that how do we better understand the human in this process? But of course, these are still first steps. There's still lots of empirical research to be done, and a lot of links to be built to perceptual and cognitive theories that are come from psychology and neuroscience. But what this will enable us, I think, is that if we understand these dynamics or the dimensions of the humans better, we will be able to design and adapt solutions to the humans. All right, I mean, with this, I'm sort of just concluding. I hope that I was able to sort of show you how visualization can sort of empower you in asking these hard questions in data science, like how and why and what if, why is this a cluster, what if I leave this feature out? And visualization is a key facilitator for that process. And then just to conclude, I'd like to argue that success in data science really requires this effective interaction between all of these components. And algorithms are there to sort of support us what we are good at, but they have a lot to learn from the human expertise as well. But we also need new techniques, better empirical evidence to understand the human and better adapt our solutions to the human understanding. With this, I'd like to thank all of these people that I've worked with over the years, and sort of happy to take on questions now.